Hello and welcome. Today we're going to be computing a volume using a double integral in polar coordinates. We're going to do a very straightforward, simple example, something that would be a first try at things like this. And here's how we're going to do it. First off, the volume is going to be defined as follows. The volume is all x, y, and z points such that z is greater than or equal to 0 and z is less than or equal to 1 minus x squared minus y squared. All right, so clearly what we're saying here is that all points are above the xy plane. So the z equals 0 plane, okay? And here what we're saying is basically, if we look at this right there, that's actually a downward facing paraboloid. Okay, so if we make a graph of this, it's going to be like as follows. There's going to be a unit circle down here, like that, and above it, the parabola sits like that. Looks sort of like that. Okay, I didn't draw that particularly elegantly, but you get the idea. All right, and you can see here, remember a circle is going to be equal to x squared plus y squared is equal to 1. That's the unit circle. So at z equals 0, of course we have 1 minus x squared minus y squared. That's what our equation shows. So clearly if I can move the 1 over, or the x squared minus y squared over, we get the following curve. And so that yields this unit circle that's on the xy plane. All right, so a good way to find this volume is going to be doing a double integral over this disk. We'll call that disk D. So there's the D right there. I'll put it in blue so you can easily see it. Okay, there's D times the function 1 minus x squared minus y squared. So we're integrating over that function. dA. Okay, so the idea here is that to compute the volume, what we do is we take a little area segment dA down there, and we estimate, we compute the height, or we find a representative point within that, the height that's going to be up there at the z value for that. And of course we'll do a lot of those little patches like so, until we fill up that entire volume. Okay, and again, that's the idea behind a double integral, is that we're computing a bunch of volumes. So basically a height, that's going to be this thing right there, times an area, and together that makes a volume. And this is add up all volumes. Okay, so that's in essence what an integral is. The question then, of course, is how do I turn this into an iterated integral? All right, so we have to answer a few questions about what these are, what all those are going to be, as well as how do we express f. And so the answer, of course, is that Euclidean coordinates are difficult to use in this case. And the reason why is, of course, we're integrating over a disk D. Okay, so it's much better is to use polar coordinates. Okay, so how do we use polar coordinates? Well, we know that dA is going to be equal to, and this is something I think every student should have right at their fingertips all the time. If you use polar coordinates, your dA, your area element is going to be r dr d theta. Okay. The other thing is that r squared is equal to x squared plus y squared. And this works really well for us because note that this x squared plus y squared is part of our problem right there. Okay, so it shows up all over the place. So anytime we see an x squared plus y squared, we can put an r squared in its place. That's clearly going to be a good substitution. Another one, of course, is r is equal to cosine theta, and that y is equal to r sine theta. Okay, so those are the ingredients to do any polar coordinate calculation. The last little bit here we have to do, though, is we have to define what D is. So D, of course, is a disk with radius 1. So we have to describe that in polar coordinates, and that's actually pretty straightforward. R is a unit disk, so it's going from 0 to 1, and theta goes from 0 to 2 pi. It has to go all the way around. All right, so all of those together, if I round up all of those facts, I should be able to now build my integral. We're going to do that on the next page. So what we have here is a double integral over d of f of x comma y dA. And now what we're going to do is we're going to integrate from 0 to 2 pi, and we're going to integrate from 0 to 1. And we're going to go from 1 minus r squared, and then our dA is going to be r dr d theta. So I've plugged in everything we need to plug in order to turn this into this is actually a computable iterated integral. All right, so now we can just go ahead and do that. And again, this is the volume we're computing is this parabola shape, like so. We want to compute what that gumdrop looking shape is. Pretty straightforward to do now, 0 to 2 pi. And then we do an integral. We should do maybe a little bit of simplification here. That becomes what we have here, of course. We have to remember that r has to multiply in to both pieces there. So we have r minus r cubed dr d theta. So we're going to integrate that first integral and get r squared over 2 minus r fourth over 4. And now we're going to evaluate it 0 to 1, d theta. And we're going to end up with 0 to 2 pi is our integral of 1/2 minus 1/4 d theta, otherwise known as, of course, 1/4 right there. And then what we do is we integrate that. So we're going to get 1/4 times theta, and then we're going to evaluate it 0 to 2 pi and end up with 2 pi over 4, otherwise known as pi over 2, and that is equal to our volume. Okay, so the volume embedded inside of this gumdrop shape, all that volume in there, is equal to pi over 2. So that's how we can use polar coordinates to compute a volume. Of course, this is all, the polar coordinates is very useful for any domain with a circle, or at least one that's best expressed in polar coordinates. So that's mostly going to be circles or semicircles or some other angle dependent shape that you can easily express in terms of an angle or or a radius. Okay, so anyway, I hope this problem illuminates a few things for you. I want to keep it short and sweet, so thank you very much, and I'll see you in the next video.